quantization in the latent space. So I'm assuming that we already are aware of vector quantized variational autoencoder VQVAE model, and this post is specifically related to the vector quantization in the latent space. So let us assume that we have some parameters. We have the output from the encoder, which needs to be quantized into one of the code books, and the decoder takes the input from this code book and processes them. So specifically, we are talking about the latent code book calculation. So for that, let's define some parameters. Let's take batch size equal to 2, number of time steps equal to 10. Let's imagine a typical application like language modeling. Number of channels output from the encoder is 16. This can be the encoder dimensions. Typically they are 128, but because Collab notebook has less RAM, I'm going to stick to 16 for purposes of this video. And let's just define a random vector for as encoder output with the shape of BTC, batch size time steps in the encoder. Now, once we have this, essentially the idea in VQVAE is to compare this to a set of code books that we have and pick the closest one. Let's try to get this least possible uh, or the most easier implementation for this. The input channels to the quantizer will be the channels of the encoder. We can, as you would imagine, put a linear layer and match the dimensions, but for now, let's just take the dimensions to be equal. Number of classes, this is the important part. The idea is to select n clusters in the latent space. So if we take language modeling or if we take image captioning as I'm trying to do in this context, there will be 80 objects because Coco I know has 80 objects. The number of classes is 80, although for computational purposes we can make this 128. The number of output channels, let's leave this guy for now. Um, and we initialize the code book using a nn dot parameter, torch.nn dot parameter, with number of channels and number of classes. Now all we have to do is to compute the difference between the encoder output and the code book. However, the shapes are not all right? The encoder output is in BTC, whereas the code book has a different shape. Therefore, a good way to do it is to multiply the batches and the number of time steps, so that, because that's kind of a reasonable thing to do. So what we are doing here is reshaping the encoder output to two dimensions with one dimension squeezed at the unsqueezed at the end, and the same thing happens to the codebook as well. We are unsqueezing one dimension, which is the first dimension. Therefore, the dimensionality is appropriate. Then we can calculate the distances of each of those encoder outputs with respect to the codebook, and then pick the minimum distance one and return that to the output. So this is how a very simplistic way of calculation of vector quantization or the closest codebook in the latent space for a VQVAE model.